Okay, so we want to talk about one more application of the derivative at a point, and that's the idea of linearization and differentials. Now, as a motivating example, let's think about the following number, square root of 17. Now, what is this number? Now, of course, you could plug this number in your calculator and get some sort of decimal approximation, but that's using a calculator. So think about it this way. How does your calculator know what the square root of 17 is? Well, it uses some sort of approximation algorithm. And the idea behind linearization is kind of a first step towards approximating things of this form. So square root of 17, for instance. And so this really goes back to thinking about the derivative as a rate of change. So remember that we had that the derivative at a point was the approximate change in a function when the independent variable changed by 1 unit. So let's think about this. Let's think about the function square root of x. So if I take the derivative and I plug in 16, this is the approximate, so this is the approximate change in square root of x, or f of x in other words, when x increases from 16 to 17. So in other words, I can say that square root of 17 is approximately equal to the square root of 16 plus f prime of 16. Because f prime of 16 is the approximate change in square root of x when x changes from 16 to 17, but that's what square root of 17 is. It's just whatever square root of 16 is plus how much I increase. So this actually gives what's called a linear approximation. And what we'll see is that the linear approximation is really given by the linearization of this function f of x at 16. So this is just kind of an example. And just to finish the example, we'll do that a little bit later. We'll actually compute f prime of 16 and see what it is. But for now, this is the snapshot you should have in the back of your mind. We want to know how much a function changes when the independent variable x changes by just a little bit. So our goal next is to make that more or less precise. Okay, so the idea behind linearization is the following. And there's really nothing new. In fact, if you can find the equation of a tangent line, you can actually find the linearization of a function. But if f of x is a function, now we also need the function to be differentiable at some point a. Because we really need the tangent line to exist at that point. Okay, so here we go. The linearization of f of x at x equals a is, well, basically just the equation of the tangent line. So L of x is what will denote the linearization, and then we'll just have f prime of a times x minus a plus f of a. So you see, this really is just the equation of the line tangent to f of x. So the graph of the linearization really is just the graph of the tangent line. So if here's the function, f of x, and here we have x equals a, then the linearization is just the linear function given by this tangent line. And here's the whole idea behind linearization. So near x equals a, L of x is not too different from f of x. So see, if I kind of zoom in just kind of right around x equals a, we see that the difference between L of x and f of x is not that great. So if I want to know what f is approximately near a, then I really can use this linearization, and it will at least give me a first order approximation. Now there are higher order approximations that we're not going to talk about, but remember, this is just a first step of getting into the approximation process using the linear or first order approximation to a function. And the reason we want to use the linearization is because lines are really easy to work with. It's really easy to compute function values of a linear function. It is not always easy to compute function values of a more complicated function. So let's give a little bit more terminology to this idea. So one of the trickiest parts about this topic on linearization and differentials is there's kind of two different ways to think about the same thing. And one is, of course, the linearization, which we basically just gave. But another way is to think about a small differential change. Okay, so let's draw kind of our toy function that we'll mess around with. So here's f of x. Looks good. And now we'll pick an x value, x equals a, for which f of x is differentiable. And let's just draw the tangent line. And now, of course, this is just L of x. This is the linearization of f of x at x equals a. And notice that's important. It's the linearization at a particular x value. You know, we could also do a linearization over here, over here. But I'm strategically picking this x value, a, for some reason. Now let's think about this. Suppose that I move just a little bit to the right. And let's say that this point is a plus dx, where dx is a small change in x. So all I'm saying, why am I using this notation dx? Well, you'll see that it sort of fits everything together in a minute. But I'm just saying, okay, maybe this is 16. I want to know what 17 is. So I know the square root of 16. What's the square root of 17? Well, I have to change by a small, sometimes called differential amount. So what can we do? Here's what we can do. Of course, here is f of a. And if we kind of follow this up put this here. So this is like f of a plus dx right here. But you see that where f of a plus dx is right here is not so far away from L of a plus dx. So if I go dx away from a and look at the value at f of x, it's not so different from the approximation on L of x. That's just what we were saying before, that L of x was not too different from f of x. So let's give a little bit of terminology. So we're going to define this triangle. This is the Greek letter delta, so delta y. Delta means change in, so delta y, change in y, is going to be f of x plus dx minus f of x. Okay, so that's like this distance right here. If I'm at a, so if I plug in x equals a, the difference between f of a and f of a plus dx is called the absolute change. In f, or in y, if y is at f of x. So we'll think about y as being actually the dependent variable given by f of x. So this is the absolute change in y right here when x changes by dx. Okay, so dx again is a small differential change, and then delta y is the absolute change in the function. Okay. Well, the idea is we want to look at the approximation to the differential change, which we'll define by dy. And now dy is L of x plus dx minus f of x. So notice the only difference is instead of using the actual function value when x changes by dx, we're actually just looking along the linearization, or the tangent line. So this is the approximation, sometimes called the linear, just to specify that we're using the linearization. So this is the linear approximation to the absolute change. Okay, but look at what L of x plus dx is. So what is L of x plus dx? L of x plus dx is equal to, well, remember that L of x was just the tangent line, f prime of x. So at x equals a, it's f prime of a times x minus a plus f of a. And so if I plug in x plus dx, then this is going to be f prime of a. If I plug in x plus dx right here, then what am I going to have? Now, if I evaluate the linearization near a, or if I look near a, so in fact, if I look at maybe this is a little bit confusing, but if I look at a plus dx specifically, then what I have is x minus a, so a plus dx minus a is just dx, and then plus f of a. Okay? So what I see is if I subtract off f of x, then that kills this part, and we see that this linear approximation to the absolute change really is just f prime of x times dx. Okay, so the derivative kind of approximates the change in a unit step, but if we just scale that by an even smaller change, so maybe we only want to change by like 0.1 or 0.2, however far away we want to look from x, well, the approximation to that absolute change is just given by f prime of x dx. Okay, so I know this is a little bit confusing, but the idea is really simple. This is just kind of another perspective using what's called differentials. So by differentials, we just mean dy and dx. So I'm just using a differential to express the linear approximation to an absolute change. Whereas before, I was just thinking, okay, the linearization is the linear approximation to the function. So it's just a matter of whether you're thinking about approximating the function or approximating a small change in the function is really the only perspective. So there's one more related concept that I want to define related to absolute change. And then I'll kind of summarize everything that we have. So recall that if y is f of x, then we have the absolute change. We just talked about that, delta y. But we can also define the relative change. Is, well, it's the absolute change divided by y. Okay, so what are we doing? Well, this is sort of like the difference between accuracy and precision. So accuracy is like delta y. That's just your absolute change. Your relative change is kind of a level of precision. You're just scaling the absolute change by your particular y value. So of course a larger y value is going to be less sensitive to a small absolute change. Okay, whereas if y is smaller, then a larger absolute change is going to make a bigger difference, so to speak. So the table looks like this. We have, of course, y equals f of x. We have the absolute change, which is delta y, is equal to what? Well, it's equal to f of x plus dx minus f of x. Okay, so this is the actual. I mean, that's actually what the absolute change is. But then we also have an approximation, specifically a linear approximation, using a differential. So that's dy. And recall that that's just f prime of x dx. So the advantage of using the linear approximation is that you only need to know the derivative. Whereas here, you actually need to know what the function is to evaluate at some point and then evaluate at another point. But here we just need to know the derivative at a particular point. And then we can also look at the relative change. Which is delta y over y. Or in other words, f of x plus dx minus f of x all over f of x. And then we also have the linear approximation to the relative change, which is dy over y, which is f prime of x dx over f of x. Okay, so we have absolute change, relative change, their actual values, but then we also have their linear approximations, which require less information to find. Okay, so let's go back to the example we had of finding the square root of 17. And now again, we want to use a linear approximation. So that requires using an appropriate linearization. Now notice that we don't have really any information. And so in reality, you kind of have to be a little bit creative of how you apply the linearization. But the idea here is that even though we don't know exactly what the square root of 17 is, we do know what the square root of 16 is. So if I let f of x be square root of x, and I let a be 16, what I can do is find the linear approximation to f at a equals 16. So what is that going to be? Well, it's f prime of 16 times x minus 16 plus f of 16. Okay, so what is f prime of x? Well, that's just the derivative of square root of x, which is 1 over 2 times the square root of x. And of course, if we plug in 16, we'll get 1 over 2 times the square root of 16, which is 1 over 2 times 4, which is 1/8. So our linear approximation is 1/8 times x minus 16 plus f of 16. But the reason we chose 16 is because we know what f of 16 is. It's 4. Square root of 16 is 4. Now remember, all this is the equation of the tangent line. So if I go a little bit away from 16, say to 17, I'm looking along this tangent line, but those values on the tangent line are close to the function values, as long as I don't go too far away from 16. So what I can say is that f of 17, which is approximately equal to L of 17, that is square root of 17. So square root of 17 is going to be approximated by the linearization evaluated at 17. And so what is the linearization evaluated at 17? Well, it's 1/8 times 17 minus 16, which is 1. So 1/8 plus 4, which equals 4.125. So the square root of 17 is approximately 4.125. And so let's use a calculator real quick. So if we take square root of 17, it equals 4.123, 1, 1, etc. So look how close this was. I mean, with doing very little work, only knowing information about the derivative of square root of x, we actually got an approximation that was correct up to 2 decimal places. And if we find the relative error, what is the relative error? Well, I just plugged it in a calculator, and I got 4.59 times 10 to the minus fourth. So we see that relative to the value of 17, square root of 17, this error is pretty good. And if you thought about, okay, this is a measurement, and maybe this is a measurement in millimeters, something like that. 4.123 versus 4.125 in millimeters is really, really small. I mean, that's, of course it depends on what you're doing, but we're already seeing that, yeah, this is a good approximation to square root of 17. Just using a value near 17 that we know the square root of and the derivative of square root of x. So this is the idea of using the linear approximation, or really the derivative, the rate of change, to approximate function values near a given value. Okay, so a very similar question here. We want to give a linear approximation of sine of 0.1. Now, the first thing we need to do, of course, we're looking at this function f of x equals sine of x. The first thing I need to do is pick a number near 0.1 that I know what sine of that number is. So it seems like 0 is going to be a good choice. So find L of x, the linearization of f of x, at a equals 0. So sine of 0 is 0, recall. We also know the derivative of sine is cosine. F prime of 0, cosine of 0 is 1. So it looks like the linearization of sine at a equals 0 is going to be given by 1 times x minus 0 plus sine of 0, which is 0. Or in other words, L of x is just equal to x. And that's pretty cool, because then we can say that sine of 0.1, which is of course f of 0.1, is approximately the linearization evaluated at 0.1, but that's just equal to 0.1. It's just the identity function. So here is our linear approximation, 0.1. Now if we use a calculator, we see that sine of 0.1 is equal to 0.0998, or it's approximately equal to that. So we could keep going. But again, look how close it is. Just to this really simple linear approximation that sine of something is just equal to that something, approximately equal to that something, it's very good. And so if we find the relative error, just plug that in the calculator, what we get is again pretty good. 1.67 times 10 to the minus third. So it's a very good approximation. And actually, this is a very important approximation in physics. So the approximation sine of x is approximately equal to x for small x is called the small angle approximation. So it has a special name because it's so important. This approximation that near zero, sine x is approximately equal to x. Now I'll just tell you one such application of the small angle approximation. So when you're looking at the motion of a pendulum swinging, so back and forth like that, it's fixed maybe to the ceiling. If our oscillations are small, so we kind of derive the equations of motion for the pendulum, and we can actually use, in one instance, the small angle approximation and actually get an explicit formula for the motion of a pendulum. So that's just an example of a time when you'd be interested in using this small angle approximation, when the oscillations of a pendulum are relatively small compared to its length. Okay, so here's a really cool application of sort of using the other perspective, not the linearization perspective, but the differential perspective, so approximating the absolute change. So you want to paint a spherical ball of radius 1 meter, and you want to apply 1 millimeters of paint around the outside. So the question is, how much paint do you need to use? It's a very practical question. Okay, so I'll tell you that the actual answer, so the exact answer is the following. It's V of 1 plus 0.001 minus V of 1, where V of r is 4/3 pi r cubed. So of course V of r is just the volume of a sphere. And now, how do I know this is the exact answer? Well, if I have this sphere and I apply a coat of paint 1 millimeter thick, well, the inner radius is 1 and the outer radius is 1.001. So 1 meter plus 1 millimeter. And of course, I just did the unit conversion. And this volume that I'm painting is just the difference of the volume of the outer sphere minus the volume of the inner sphere. So that's where I'm getting this from. And we could do that using a calculator. But I just want to approximate this, okay? And hopefully I can do a good approximation. So to approximate this, I can use a differential. And now recall that this is actually equal to delta V. So I want to approximate delta V by the differential dV. And now remember, dV is V prime of r times dr, where, of course, my dr is the amount the radius is changing. So that's dr. And we can also figure out what V prime of r is. Well, just take the derivative. We get 4 pi r squared. And of course, we're interested when r is equal to 1. So we start at r equals 1. R changes by dr, which is 0.001, 1 millimeter. And this is the approximation to the absolute change. So dV is V prime of 1, which is 4 pi, just plug in 1, and then times dr, which is 0, this is dr, v prime of 1 times dr, which is 4 pi times 0.001. So basically, it's the surface area and then scaled by just this small change, is another way to think about it. And so what do we get? Well, we get approximately, well, you're going to get this. Now this is, of course, meters cubed, but if we convert that to, say, gallons or liters, this is about 12.6 liters or 3.3 gallons. So that's about how much paint we need. And this is going to be a really good approximation, okay, because the differential change in the radius is very small. So we would expect the change in the actual volume to be very, very good. So if you were painting something and you wanted it to be about 1 millimeter thick, and you didn't want to get an exact value of the amount of paint you needed, you could definitely just do a really quick linear approximation and get, okay, well, I need about 3.3 gallons. But that at least tells you, okay, well, I just need to go get 4 gallons and I'll have plenty of paint. Whereas before, you may not have had any idea. Okay, so here's another example, but this time we're not going to be looking at absolute change. We're actually going to be looking at relative change. Now I know that's the case because I'm trying to compute or calculate something within 3% of its actual amount. So 3%, that's a relative change because it's the absolute change scaled by however big it is. So I would like to build this tank, and here's the volume of the tank, the relationship between the height and the volume. And so we know the height and radius are equal, that's why this is the formula. So I would like the volume of the tank to be within 3%. So what that means is that I want the relative change. So the change in V, absolute change in V over V, to be less than 3%. Now I know that I can approximate the relative change by the differential dV over V. Okay, so what does that mean? Well, what is dV over V? Well, remember that dV is just V prime of H times dH. Okay, because I'm looking for the change in volume as the height changes. Okay, so I just scale by this dH, dV is V prime of H dH. So dV, what is V prime of H, first of all? That's just going to be 3 pi h squared. So we have dV is 3 pi h squared times dH all over, well, V, which is just pi h cubed. Okay, so look at all the stuff that cancels. The pi cancels, those two h's cancel with 2 of the h's on the bottom, and now I actually have that dV over V is 3 times dH over h. Okay, and I can just take the absolute values of both sides, and I see that this dH over h is approximating the relative change in the height, which is exactly what I want. I want to know how precisely, or to within what percentage of its true height, should I measure the tank's height. So I would like this to be less than 3%. But then look, that means that dH over H, if I just divide by 3, should be less than 1%. So I want to measure the height within 1% to guarantee, well, to approximately guarantee, that the volume of the tank be within 3%.